Hello guys, in this video I want to talk about binary heap again. I will do some modification in the previous implementation of our binary heap. So, first thing I want to say that our previous binary heap video have some problems. If you don't see it, you must see it to see this video. Because previous video was about main ideas of the binary heap. But now I will do some improves in the interface. This improves needed because at some future videos I want to make a Dijkstra algorithm implementation in Haskell. And to speed it up, I need to use binary heap. So, let's start. First of all, look here. Here we have some binary heap. And the nodes here is pairs. I make pairs because in the previous video we do only case. And this leads us to problem that we can't distinguish nodes with the same case. But here we have pairs. The first element is the key of the node and the second element is the node identification. So I assume that the second element is always unique. So this is the node identification. Okay, and here I add some type class. Which type class represents some kind of container. I will call it heap container. So this is some abstraction which allow us to abstract from different internal implementations of a binary heap, such as a list or so on, or map, and it allows us to work in a nice way with the binary heap using only this abstraction. And at some point we can go to this abstraction and implement its details. Way can be fast or not. So let's talk a little bit about this abstraction. So here we have some container. It's just container. You can think about it like an array or map. Okay, the main thing which it provides, it's provide us a relation between indices and the elements. So it's in some way somehow a list, and we can ask first, this is some type which here represented as a some abstraction C, and this type has some, this is a polymorphic type of kind star to star to star, and a first parameter is a case of this container and the second parameter is a nodes. So actually it's mapped the case to the nodes. Okay, I assume here that the n is always unique, Okay, and we mapping the case to nodes. So let's look at some functions of this type class. The first function is empty. It just creates an empty container of type ckn. The second function is a length function, which takes some type of this container and return the length of it. This function append, which takes some k, takes some node, takes some container and returns a new container. There we append the element, this key and this node, to the end of this container. So if you look at this example of the tree, the case here, these numbers, the key type, and the end type is this is a char. So this characters which identifies every node. Also, we have this function get I by n. This function extracts to us the index of a node of type n in this container. So index is represented as an integer. So here at this point you must understand that we represent our binary heap as a complete binary tree, and we store our complete binary tree as an array. Okay, we go from top to down and from left to right we fill this array. And you can I already do some markers here about how the left and right childs are represented in this array. So if we know the index of some node, we can calculate the left child index and the right child index, and so on. We can traverse on this tree, on this binary heap. Okay, and here by the node we can extract the index also. So if I have D, for example, here, I can extract the index in the array which internally represent this binary heap. So I extract not this k3, I extract the index. Okay, go next. Next function is look like this. It's represent like operator, and it takes some container and the index and retrieve the pair. Actually, this is this pair and this container. So the pair has some k and the node. And the second function get exactly the same, but it returns to us the maybe type, because we can ask for index which is not in this array, and in this way we return the nothing here. The next function is set. It takes some integer. This is the array index, and it takes some pair, the key and the node identification, and it's modify this container and returns a new container. And main function which allow us to manipulate the binary heap is the swapping function. Okay, it takes two indices and the container, and it exchange elements by these two indices in the container and returns a new container. And also the last function is extract last. This is a function which take the last element from our container array and return to us a new container without this last element and this element itself. So we return a pair, and of course it has maybe here because it can be such case that our container is empty, and in this case they return nothing. And interesting that we can implement our function swap here in this type class, because if implementation provides to us s and get functions, we can provide swap, and I use this thing here and implement this body of this function in this type class, and we don't need to implement it later in any of the implementations. So In the previous video about heap, the first video, actually we represent our heap as a list. But now we go to the next abstraction level and we represented this type class, heap container, C. Okay. And now let's implement some data structure which implements this type class, so which provides to us this type class. I will call this data structure CR, so it's somehow container array. And container array is a pair of two things. The first thing is a list, which represent the keys and the nodes of our heap. And the second element is map, which represent the mapping of nodes to the indices of this list. And you may ask why you need this second data structure. And the answer is I need this data structure to speed up my operations. And I use some kind of denormalization here. Of course, during the implementation of these methods of that type class, I need to provide constraints between these two data structures, between list and the map, because they somehow duplicate the data. Okay, and you may ask which things you want to speed up. The problems here that I want to, in this video also, I want to add two operations into the binary heap. These operations allow to modify the case of the nodes. And because in the previous video our heap consists only of the case, we can distinguish the two nodes we can't distinguish two nodes with the same case. But here our case is pairs. And then I want to modify some node. I need to provide its identifier. And its identifier is actually the second element of this pair. So this is, in this case, this is some char. For example, I want to modify this node. I will provide some char x here and the new k. For example, I can change this one to 100, or I can change it to 0. And every time if I increase this k, I need to use one operation. And when I decrease this k, I need to use another operation, and we will talk about these operations a little bit later. But now let's continue to review our implementations. So here we have the instance for our container, heap container for CR data type. And you can explore this implementation. I don't want to talk about it now. I think it's very simple. You can find this link in the description with this code and look at this more carefully. The one problem here no, let's talk about another thing. So we have this mapping. This mapping maps the nodes from the n type, this is the chars in this example, to the int. Okay, if I haven't this map here, This leads me to this thing that leads me to that I need to traverse all this list to find the node. And as you know, in this case, the time of this operation will be the big O from n. But this mapping, I can find the list index with log n time. Okay, and that's why it's speed up. So I can now search for case for these chars with log n time and extract its case from this list. So I will know the index from here, and by index I will extract this information. But the problem here is that the list itself it's not very fast for access for index. By example, we need to traverse at the worst case all the list. And then the insertion also, we need to rebuild the list. Okay. And that leads me that I need to replace this list here with mapping. And for this I create a new data type. I call it container array implemented there maps CRM like this. Of course it take case type and nodes type. And here we use not list but map. So actually I use a map here like a list. So I provide the mapping from some integer case to the values. So exactly this is exactly that the list do. But the map I can extract these indices elements by this indices much more faster. So with log n time against n time. Okay, and here we have this implementation of this for container type class. We have this implementation. So, and you can explore this implementation by the link in this description. But actually you didn't need to go to these details. All thing you need to know is that we work in this abstract type class. But the implementations with two maps is fast enough. Of course, they can be increased by using not data map but the hash map, I think, and then in this way they can get the constant time of the main operations. I think all operations of this type class. Now let's review the modifications which I implement in the binary heap implementations. So the first function I want to start is heapifyup. Actually, this is the ins function from the previous video. This function allows us to insert the elements into our array. In the previous video this was a list, but now this is our container of with type class constraint as heap container. So we take this heap container, we take some element index in our container, and they do heapifyup. So when they do insertion, the add element to the end of the array provides its index, and they do heapifyup when they go to the root. So we check that if our parent is greater, then they exchange, then they do swapping, and check this thing again in our parent, and so on until we come to some point that our parent is greater or equal than our node, current node, or then they go to the root. And they use this heapifyup function in our insertion function. We append our container, the k and node pair here, and we run our heapifyup with the last element of our container. They provide this in here. Okay. Here we have some function which construct the heap from a list, the heap of this type. So we provide a list of pairs that they have the elements case and elements identifiers, and they build this container. The next function I want to review is heapifydown. Actually, this is our HP function from the previous video. I do some optimizations here. I provide the tail call recursion here to somehow speed up this thing, and also I'm using the do notation. This allows me to simplify the code a little bit. In the previous video I think there was some extra join here of removing some layer, but here this is done via do notation. So actually here they look some cases when the heapifydown, this operation is used, then we extract the maximum of the heap. So they put the lastest element of our container they extract the first element of our container, and we replace it with the last element of our container. Actually, they do this with swap function, which we provide in the this type class #cont. And here they do heapifydown. So when our last elements go to the root of the tree, they need to heapifydown, and they here ask for these cases, then the left and right nodes as equal or greater or lesser, and we somehow look at these cases here and provide a swapping and go on to our recursion. Okay, and here you can see the extractmax function. We provide some container which represent our heap, and maybe we return the, if it has some elements, we can return the maximum element and the new heap. And of course, how can we do this? We use the swap function, which swap the last element of our container and the first element of our container, and provide our container. And then they extract the last element, this is our maximum, and they use this container to provide heapifydown. Okay, we call here heapifydown, started from a root. This one identifies the root in our container, and they do heapifydown, provide to provide the all the consistency of our heap. Okay, and here let's look at these functions. This is two functions which I add here, which allow us to modify the nodes of our heap. The first function is used when we want to update the node of our heap to less k. In this case, if we decrease the k of some node, we need to provide heapifydown, okay, because its parents can be greater after this operation, and we need to check that we need to somehow pop up our parents. And here we run our heapifydown function with some new container and some index. The index we get by get I by n function of our hashcount class, and we can know now we can define the index in the container of our node. Then we just use set operation to modify the node in our container, and after we modify it with the new lowest k, we now can heapifydown in our tree to provide the consistency. And also updating our element to greater k function. It takes some container, it takes some node identifier and a new k, and provide to us a new container. And what we do, we setting the construction a new container. This new container, there we set this new node pair with a new k and the same node, and we extract the index of our node by this function, and then we do heapifyup because our node is increased. They need to check the thing that our parent is less than the new node, and that's why we go up. We do exchanging and so on with our heapifyup function. Okay, and these all the methods that we need for our binary heap to work with. And now we can use this heap, for example, in the dextra algorithm to speed it up. And now I want to provide some examples of how can we work with this function. Okay, we start from the construction of our binary heap. So we have this function, build heap from a list, and we can use it. Here I take it from here and run it in my CI, and as you can see it, so I need to provide type here of my container, because here is abstract container, but here I provide some type, and this is the type, this type. Then there we use two maps, so this is actually this type. And you can see that this function is built to me. So wait a moment. This function is built to me this value of this type, and this value consists of two maps, the first map and the second map. The second map is representing the mapping from nodes to the indices of this array. So this, what it means? For example, if I have the node A here, the index 4, this means that to know the k of this node, I need to go in this array and take the element this with 4 index. Actually, this is map, but we're reviewing it as array. So here I found this node, and you can see here the normalization. We found this A again, and it has k1. Okay. When I build this this value, I can transfer it to a tree. I have function. This function ct convert to tree, which convert to binary tree of these pairs of k and n. Then I transfer it. You can see I have this tree now, and I can print this tree with my print function. And all this thing represent me that this is a correct binary heap. You can see here all the elements is all the child elements is less than its parents, and this is a complete binary tree, as you can see. And now we have this tree, for example, okay, and now I can use some operation on this tree of my new operation. For example, I can update some node k to lower value. For example, if I take the node A and update it to 0, so we have node A here, and you can see that it has k1. But what happened if I update it to 0? So I take my heap constructed this expression and push it to this function, provide the node identifier and provide a new k. And here you can see that they receive a new heap. So here is A is changed to 0. But what if I want to increase it? What if I want 100? This means that our A now needs to bubble up to the top. Okay? Why it's not bubble up? Sorry. I do it in the wrong place. So I need to change it to 100 here, and it's not bubble up. That means that we have a problem here. And what's the problem? The problem is that I use the wrong function. I increase the k, and this means that I need to use update to great element function. So in the case of binary heap, then they modify the k, they need to answer the question, do we increasing or do they decreasing? And for every case there is a specific function. Okay, let's run the great, update to greater value. And you can see here that our heap is modified and our ace goes to the top because it becomes the maximum element of our heap. And it's done pretty fast because they use the mapping data structures. Okay. Of course, we can extract the maximum value of our new data structure. We can use extractmax function. Let's look at this function. which takes some container and provides a maybe pair of container. So if I extract this, for example, from here, I need to extract the value from maybe from just function, and then I need to take the second element, I think, and then I can transfer it to tree and print it. So yes, you can see here I extract the main element and the built a new heap from here. The 11 goes to the top, and we have this tree. Okay. But we check this update to greater function. Let's also check our update to lower function. What if I want to update to lower of our tree? I will take the maximum element is Z, and what if I push it to 0? Okay, change it to 0. In this way our root node needs to go at the bottom. So we have this tree, initial tree, and now I change it to 0. You can see that our Z now is at the bottom. It is the minimal element. So this means that our update to lower function works as expected. So we extract max, the update to lower, update to greater, and also we use our insertion function in this build from list. And that's all the function which we need to work with our binary heap. So let's also check the insertion function in an explicit way. What if I have this binary heap and I want to insert? I need to then insert, and I need to have container. It has here, and also I need to provide a new pair which I want to insert. What if I want to insert a new pair with K200 and some char, let's say W? Okay, and you can see we have a new tree. The W goes to the top because it has the maximum element, and here all the binary heap consistency is holds, so it works. So guys, I think that's all. Thank you for watching. Push like button, push subscribe button, and write comments if you found any errors. I do not do any testing, just types and logic and Haskell. So thanks for watching and see you in the next video. I think this will be a video about the extra algorithm.